So, good evening, ladies and gentlemen. I'm delighted to see that we have a full auditorium in this beautiful summer's evening, that you've given up the sunlight to come and listen to a talk about more interesting light, perhaps, synchrotron light. My name is Neil Calder. I'm the Director of Communication here, and it's my joy to introduce tonight our speaker, Herman Winick. Herman is one of the outstanding scientists in the world in the field of synchrotron radiation research. That Herman first saw the light in 1962. And it changed his life. And he's been working in the field ever since. Herman has seen our own lab here, the Stanford Synchrotron Radiation Laboratory, grow from the first tiny parasitic use of a high-energy physics machine to its position now as one of the outstanding leaders in research in the world. And Herman has had a great deal of, well, should get a lot of credit for its position. He was deputy director of the lab for many, many years. Scientifically, his qualifications are outstanding, but something you probably don't know about him, but I know about him, is he's also an outstanding athlete. That every year we have a hotly disputed race where we race up and down our 2-mile-long linear accelerator, and for the last 4 years, Herman has come first in the oldest runner in the race competition. So, good luck, Herman. Long may that continue. My admiration for Herman is such that, in actual fact, I'm trying to develop the same look with the beard and the grey hair and the glasses, but I'm not quite there. So, thank you all again for coming. I'd like to use this opportunity for a publicity plug. We have public tours here at SLAC. We would be delighted for any of you to come on one of these tours around our facility, and there will be people at the end of the talk who would be only too happy to fix this up for you. And now I'll hand over to Herman Winick.
Thank you very much, Neil. Thanks for the admiration. I've also admired Neil. In fact, he gave the first of these lectures to a packed house as well, and he's a hard act to follow. I told him that I would emulate him by maybe mimicking a British accent. But I want to thank Neil for arranging this wonderful public lecture series and for inviting me to give this one. I'd like to thank him and many other people for their help in putting the material together that you'll see. Everyone in the communications department that Neil heads, particularly Joni White and Emily Ball. At SSRL, many people helped me. I'd like to acknowledge Ann Mueller and Amy Rutherford. The scientific staff, I bugged a lot of people on our staff for material, particularly Uwe Bergman, Paul Fizzackerly, and Bob Batterman. So I'd like to acknowledge their help and several others perhaps who I haven't mentioned. Anyway, I'm delighted to have the chance to tell you about an extraordinary field of research that actually is based on a waste product that comes from the development of colliding beam machines for high-energy physics, the storage rings that SLAC has built. What I will tell you about is shown here. This is a list of the topics, the questions that I will try to address. And as Neil said, after the talk, there will be scientists that you can see because they're wearing their badges, and they'll be happy to answer questions that you may have, as I will as well. We also have some demonstrations here, some of which I'll show you during the talk, but most of which you can come down and see, and I'll point them out as I go along in the talk. So what I'm going to talk about is what is synchrotron radiation, how is it made, how is it used, and why is it revolutionizing so many branches of science and technology? What does the future hold? Because we're not resting on our laurels. SLAC, SSRL, has been a pioneering laboratory setting standards throughout the world and spawning activities around the world that I'll tell you about. But we have plans for the future. In fact, to use the linear accelerator to make perhaps the most extraordinary source, an X-ray laser. I'll tell you about that at the end. But there's another question that I'd like you to pay attention to. And by the way, these questions will be part of a quiz that you'll be given at the end, so please listen up. But the last question that you may be interested in is, it's a serious question. You'll see in a minute. Whoops. It is not advancing. Oh, there it is. Okay. The main instrument at SLAC, as you know, is this incredible 2-mile linear accelerator, conceived of by Professor Panofsky more than 40 years ago, and still, even 40 years later, the world's highest energy, longest electron linear accelerator in the world, and the backbone for everything that we do here, both in high-energy physics and in synchrotron radiation. It was a very visionary machine, and I think it has set the stage for some extraordinary work at this laboratory, both in high-energy physics and using synchrotron light. SLAC started out as a high-energy physics lab and pioneered in the development of these electron accelerators, the LINAC, and then storage rings that I'll tell you about, because these are the instruments that elementary particle physicists used to study subnuclear matter and answer questions about matter, space, time, energy. You may have heard recently of the concern about dark matter and dark energy. These are things that can be studied with high-energy accelerators. And SLAC has broadened out with an Institute of Astrophysics and Cosmology because the super small, the subnuclear realm, and the super large, the universe, are coming together and can be studied with high-energy accelerators. But what I'm going to talk about is the fact that the synchrotron radiation division of SLAC has now used these accelerators in an extraordinary way as very, very powerful sources of an extraordinary light, including X-rays, called synchrotron radiation. With this light, we study not subnuclear particles and not the universe. We study more common materials, but on the atomic and molecular length scale. So they're not super small. They're pretty small, as you'll see. Atoms and molecules are very small. We can't see them. We need to use X-rays to see them. SLAC built SPEAR 30 years ago, more than 30 years ago, and it was built as an electron-positron collider, shown schematically here, where positrons are injected in one side, electrons in the other. They circulate around and they collide, as shown schematically in this figure. But as the electrons curve, they emit synchrotron radiation. This is a basic fact that can't be avoided. So the particles, as they curve around, are actually losing energy, and they have to replace this energy. It's a waste product. It's something that they would like to get rid of. But it has turned out to be the basis for everything that I'm going to be talking about tonight. In the early days of SPEAR operation, many discoveries were made. New particles, the tau particle, the psi particle, leading to Nobel Prizes by Bert Richter and Martin Pearl, shown here. This is Bert Richter, Marty Pearl, colleague Gerson Goldhaber from Berkeley, back in about 1976 when these particles were discovered. This is the SPEAR storage ring today, or actually a few years ago. You can see the curving arcs, which allow the electrons to go around and generate this radiation. It's now, instead of being used for colliding beam research, it's used exclusively to produce this radiation. This waste product is now its main function. So what is synchrotron radiation? Simple answer, it's light that you can't see. It's also called synchrotron light. And I'll try to use that word because some people prefer that to the word radiation. But radiation is light. Electromagnetic radiation is light in many different colors and forms, some of which you see, some of which you can't see. But really, in more detail, what is synchrotron light? It's very intense light, including light that we can't see, and it spans a range of colors, including the visible. We don't use it much in the visible because lasers like this pointer are much more powerful sources in the visible, it turns out. But in the infrared part of the spectrum, the ultraviolet, and the X-ray part of the spectrum, synchrotron radiation is the most powerful source available. I like to compare it with the audio spectrum. We have an electromagnetic spectrum of light that goes both ways. I'll show you in a minute. there's also an audio spectrum of sounds. You know that there are sounds that we can't hear. We have evolved with eyes that see visible light, ears that hear audio signals in a certain frequency and tone range, but there's ultrasound. Animals can hear sounds that we don't hear. Dogs hear higher sounds, higher pitch sounds. Bats echolocate their prey with very high pitch peaks. I'll get back to that in a minute. The X-rays that are produced in synchrotron radiation are essentially identical to those produced in ordinary medical and dental X-ray machines that you're familiar with. But the important thing is that their intensity is more than 1 million times greater. This is the primary fact that we have used, and that means that synchrotron light enables scientists to do experiments they've only dreamed of. Things that would have taken months or even years to acquire the data can be done now in minutes. This is the remarkable thing about the radiation. And we're living through a revolution in science and technology due to the availability of such incredible performance. And this revolution really started here at SLAC back in 1974 when we turned on our first beams. Let me go back a minute and talk about the audio spectrum because you may be more familiar with that. There are sounds that you know we can hear. We talk about vibrations per second or cycles per second. 1 hertz is 1 vibration per second. The audio spectrum goes from 10 or 20 hertz up to 5 or 10,000 hertz. We have a demonstration that people will show you of sound, including ultrasound, sound that you can't hear. For example, you may know that A above middle C on a piano. Piano is here. Here's, let's see if I get this right, D, E, F, G, A. Those of you who have perfect pitch know that that's 440 vibrations per second. You can hear that. But you can't hear sounds that are above about 10 or 15,000 cycles per second. However, those are very useful sounds. It's called ultrasound, and as you know, ultrasound can be used to take images. This high frequency corresponds to very short wavelength, and this short wavelength allows images to be made, including, for example, a fetus at 9 weeks in the womb, non-invasively. Extraordinary medical development. And what's required is sound not at 20,000 cycles per second, 20,000 hertz, but 5 million cycles per second of that order, with very short periods, very short wavelengths, in order to take this image. So the point I'm making here is that different parts of the spectrum can be used to get information of different kinds. For sound, there's ultrasound. For light, there's X-rays. The increase in performance of these X-ray sources due to synchrotron radiation has been extraordinary. It's shown here since 1960, actually from about 1895 when Röntgen discovered X-rays, as I'll get back to in a minute, until about 1960, there was hardly an improvement in the performance of X-ray sources. Starting in 1960 or so, with the advent of synchrotron radiation, actually in the early 70s, it just zoomed with the development of new machines and special devices that I'll mention. You know how important the increase in computing speed has been. It's revolutionized our lives. Science, technology, everyday life has been severely impacted, very positively, by this factor of 1 million increase in computing speed of our computers over the last 40 or so years. But that's hardly anything compared to the increase in performance of this parameter called X-ray brightness, which is a factor of 1 billion times 1 million more. And it's shown schematically here. This is really an extraordinary development. What about X-rays? What are they? Do they have a size? Yes, they do have a size. We call it the wavelength. This is an important concept. If you want to see objects of a certain size, you need to use light or sound in the case that I showed you of the ultrasound image. You need to use waves, light waves in this case, whose wavelength is that size or smaller. This is a fundamental fact of nature. What is the wavelength of light? Here's the electromagnetic spectrum, like the audio spectrum, but notice how small a slice visible light is. Very important to us because that's how we see things, but in fact, light goes on to longer waves, shorter waves. If you want to see things like a cell or larger objects, you can use visible light. If you want to see things like a virus or DNA or atoms, you need shorter wavelength light. That's what X-rays are, basically short wavelength light. And synchrotron light, synchrotron radiation spans a very large spectral range here, offering extraordinary opportunities to do research over that spectral range. So what is the size or wavelength of an X-ray? The simple answer is that X-rays have a wavelength in the range of 100th to 1 nanometer. Nanometer is 1/1000th of 1 meter. It's about the size of one atom, or a small collection of atoms. Just to give you an idea of what that is, a human hair is 30,000 nanometers in diameter, about 100th of an inch. And we're talking now about X-rays which have a wavelength of the order of 1 nanometer or even shorter. I said it all started a little over 100 years ago in an extraordinary story. Wilhelm Röntgen was doing what we call now basic physics research in his laboratory in Würzburg, Germany, when he stumbled on X-rays. He had a very crude laboratory. His interest was not in X-rays. He had no idea. Nobody knew that X-rays even existed. He was studying a basic problem in physics having to do with how electricity is conducted in gases. And he built a machine to study that, which turned out to be a very crude X-ray source. And to his credit, when he stumbled on X-rays, instead of wishing that it was something that would go away because it was interfering with what he was doing, he stopped his work and started to study this new phenomenon. He was a brilliant physicist, brilliant experimentalist who did not ignore an observation that he did not expect. Imagine what went through his mind when the only person in the world who had an X-ray machine now, he is Röntgen, in his laboratory. He puts his hand in the beam and sees his bones. Can you imagine what went through his mind? This is a picture he then took of his wife's hand. People believe, we're not sure actually what that is. But he did an extraordinary thing. He realized the importance of what he discovered. He locked himself in his laboratory for several weeks. I understand his wife passed him food on occasions. And he studied all the properties of X-rays. He put in paper and cardboard and wood and steel and lead and determined the absorption of X-rays, that it doesn't go through heavy materials like lead, but it goes right through wood or paper very easily, goes right through the soft tissue of your hand. So he studied and actually then published essentially all the properties of X-rays. The remarkable thing is that many other people who had similar apparatus in their laboratory studying electrical discharges in gases had also stumbled on X-rays. For example, they would have a package of film. Film was a common thing that was used in those days. And of course, you protect the film. I mean, X-rays can fog film, as you know. Light exposes film. X-rays are a form of light. They didn't know about X-rays. They had film in a box or in a dark paper wrapper in their laboratory. And when they finally got to use the film, they discovered that the film was fogged. Instead of asking what caused the film to be fogged, they sent it back to the manufacturer saying, you sent me a defective film, please replace it. Röntgen was the only one, when he saw this faint glimmer of glowing light on a scintillation screen, he said, he's got to find out what that is. This is an example of what we call today curiosity-driven research, in the sense that it was not, the objective was not to discover something important to medical science, but in fact just to answer questions that piqued Röntgen's curiosity. Imagine if the government wanted to promote science and research to develop new medical instruments, and they called for proposals. What would they get over 100 years ago? Someone might send in a proposal to indicate how you might build a sharper scalpel or make better stitches. Röntgen would not even submit a proposal because he wasn't interested in medical applications. He was interested in the basic physics of electricity conducted in gases. So he wouldn't even have submitted a proposal, and yet he made perhaps the most important medical discovery ever. I think it's important to think about that because this is the kind of work that goes on mostly here at SLAC, in elementary particle physics, in material science with synchrotron radiation. we ask questions about the fundamental nature of matter. Most of it is curiosity-driven. Some of it is applied and very oriented, as I'll tell you, to certain specific objectives. But the most exciting work, in my opinion, both with synchrotron radiation and certainly in elementary particle physics, is what you could call curiosity-driven research. People want to know what nature is like. X-rays turned out to be an extraordinary tool for so many areas of science. One measure of that is the number of Nobel Prizes. Röntgen himself got the first Nobel Prize in physics in 1901 for discovering X-rays. Many other prizes that you know, for example, in 1962, Crick and Watson and Wilkins got the Nobel Prize using X-rays, X-ray data, to determine the double helical structure of DNA. It was determined with X-rays. Many other examples that I don't have time to go through here, but this is just one measure, if you like, of the importance of X-rays. How do we make synchrotron light? The simple answer is we do it by accelerating electrons. Electrons are very large, very light particles, among the lightest that we have conveniently available. And this shows an example of how electrons running up and down in a radio antenna or in your cell phone antenna. The electrons are running up and down, and they're accelerating. They're starting, stopping, reversing direction, just like you would be in a car or in an elevator. You sense the acceleration or deceleration, starting and stopping. This is called linear motion, linear acceleration or deceleration. When electrons undergo that kind of motion, when they run up and down in a radio antenna, they emit radio waves. They emit it all over. You want to cover a large area so that everybody's radio picks up the signal. The point I'm making here that radio waves are nothing more than long wavelength light, as I showed on the spectrum. You can't see it. The radio receiver sees it. Just like X-rays can be seen by film, you can't see it. So there are receivers, ways in which you see different colors of light, long wavelength radio waves, short wavelength X-rays. Now, getting back to accelerators, I showed you the Spear storage ring. Electrons are curving around. It turns out, as you know, if you think about it, that there's another type of acceleration, and that is when you turn a corner. If you, in a car, turn a corner particularly rapidly, you feel yourself being thrown out. Circular motion is accelerated motion. And in fact, circular acceleration turns out to be particularly effective in making radiation, particularly when the velocity of the electron that's doing this is very high, close to the velocity of light, when the ratio is close to 1. When the velocity is rather small, the radiation comes out much like that radio antenna in all directions. But two things happen when you get to velocities close to the velocity of light. You may know that the velocity of light is the maximum velocity that you can attain in any system. So when the velocity gets close to the velocity of light, the radiation comes out in a very narrow forward cone. Also, the amount of radiation made goes up astronomically, it turns out. Not only does it go up in total amount, but it's all concentrated in this laser-like concentrated stream or forward plume. So if you put a small sample here, and some of the things people want to study, biological samples, materials of different kinds are very small, you get this factor of 1 million or more X-rays per second on that sample here than you do in a conventional X-ray tube. The electrons in Spear travel at 99.99999% the velocity of light. They're essentially going with the velocity of light. If you go to higher energies than Spear, you add a few more nines. You never reach the velocity of light. This is a fundamental limitation on any particle that has mass. But they're going awfully fast, and that means that their radiation comes out in a very narrow forward cone. So when Spear started operation in 1972 for colliding beam work, it was realized that this radiation was coming off. We started our program. I came to Stanford in 1973 to work with colleagues here to develop this radiation. We built our first beamline taking some radiation from one of these bending magnets. There are some 36 bending magnets in the original Spear ring. Each one bends by about 10 degrees. 10 times 36 is 360. You make a complete circle that way. And a small fraction of 1 degree of radiation from one bending magnet was taken out into a small building about 40 by 60 feet, and we set up some experiments here. It was a risky venture. We didn't know if it would succeed because the main program on the spear ring was high energy physics, colliding beams. This was a secondary or parasitic program. We thought if it was successful, we may get support to build a second beamline and an extension here, but we had no idea how it would work. But we made good use of a waste product, I would say. This is really the point, that this was not radiation that was of any interest to high energy physicists. We made use of it. So I worked intensively with my colleagues here for a little over a year in building this building and getting the equipment all together, and all hell broke loose when we first turned on the radiation. Incredible results started coming out. This factor of 1 million that I talked about was immediately opening up areas of research that brought people in from all over the world to use it. And that meant that we had a lot of work to do. So for that whole first year or so, it was just day and night working, building the equipment, and then working with users to use it. Finally, after a year, we had come here in '73, and sort of by mid-'74, my wife said to me, "We've been here a year, why don't we go visit San Francisco?" I said, "Okay, I'm busy, but let's take a day." So we went to San Francisco. What did I see in San Francisco? One of the first things I saw was this. And I said, "Eureka! My God, if we can teach electrons to go through curves like that, essentially a succession of bending magnets, then the radiation from each one of these bumps would add up in the forward direction, and we'd get even more than this factor of 1 million. What a neat idea." So we rushed back and we started to build what we call wiggler or undulator magnets, the first one of which is shown here. It's on display outside now. It was built in 1978. And essentially, it's a succession of alternating north-south poles, which this is only half the magnet. There's another half goes on top. Vacuum chamber goes through it. The electrons, when they see this alternating periodic field, do this wiggly motion, and that makes even more radiation. It was then pointed out that you could make these alternating fields with simple blocks of permanent magnet, and that led to an even more important concept, because these small permanent magnet blocks, you could pack many more alternating poles in a given length. This is called the undulator. So we built the first wiggler in '78, the first undulator in 1980, and that set the stage for how machines are built now all over the world, to optimize them for the use of these so-called insertion devices, which fit between the bending magnets. The bending magnets are still brilliant sources of radiation, but in the space, the drift space between, you see these wiggly lines. You can put wigglers here, here, all around, and you can then make these machines and put as many of these wiggler or undulator magnets in them, and they generate even more brilliant light. The way a machine works is shown schematically here. The electrons start in a small linear accelerator. They're then injected into that booster ring, transferred to the storage ring, and as they go around, they light up. The radiation coming off the bend magnets and the wigglers or undulators, which are not shown here, go down these beam lines and into these hutches, these small boxes or rooms in which experiments are set up. So this is a schematic which shows that sequence of events. There are only a few of these experimental hutches shown here. At SSRL now, we have 33 of these boxes around the ring. 33 experiments can work simultaneously and independently. It's essentially a research factory. It's extraordinary. The end of the beamline is this experimental hutch, and here's a picture of one. It's basically a little box, steel box, sometimes lead-lined. When it's open, the experimenter can go in, put his sample in there, close the door, reset some interlock systems, which make sure that nobody's inside at the time, and then carry out the experiment with the controls shown here. So we have 33 of these stations here. The laboratory has grown from that single one beamline that I showed you in 1974. We built additional beamlines. We now have about 1,800 users from 200 institutions in 11 countries. Most of them actually come from the major research universities in the United States and around the world. People who are doing, as I said, curiosity-driven research. But in fact, we serve a lot of industrial interests too for what we would call applied research. For example, one of our programs that I'll mention later involves companies such as IBM, Intel, Motorola, Philips, Advanced Micro Devices. And these companies are all interested in using X-rays to understand how to make cleaner silicon wafers. You may know, here's an example of a silicon wafer, an 8-inch silicon wafer, and I'll show you another picture later on of an even larger one. You can come up and look at that. These are the wafers on which small integrated circuits are made, and that's what drives the computers that you all use, the personal computers. So I just wanted to point out that we do a lot of work that's of interest to industry, the semiconductor industry shown here, and also the pharmaceutical industry, because they use X-rays to understand viruses and toxins, and they use that to develop drugs. And I'll get into that a bit more later as well. And here are some of the pharmaceutical companies that use SSRL. So over the years, from 1974 to this year, the laboratory has grown. You see the growth in the number of users. We're pushing 2,000 now. And instead of just this one beamline in one small building, it now goes all around the ring. We take radiation from many bending magnets and even more wiggler or undulator insertion devices. And it's a major national user facility. Users are scientists that come from all over the world. And that led to a desire to upgrade the machine and make it even more powerful, because remember, the machine was designed by high-energy physicists for colliding beam, high-energy physics, elementary particle research, not as a synchrotron light source. And in the intervening decades from 1974 to today, we've learned how to make these machines that generate even more radiation. So we obtained money from the US Department of Energy and the National Institute of Health to remove the machine that had been built 30 years ago and replace it with a new machine. This is a time-lapse video which shows how fast it can be done. But removing the old machine, pouring a new floor, putting in the modules, the pre-assembled, pre-aligned modules are being brought in quickly here. So you see, compressed in a few seconds, 6 months of very, very hard work by hundreds of people. This shows some of the equipment as it was being assembled. There are the various magnets. And by the way, I have cross-sections of the various magnets. The main magnet is the so-called bending magnet or dipole. Imagine a vacuum chamber in this gap. This is a north and a south magnetic pole. Magnetic field is this way. It makes the electrons curve. And this is a cross-section. These are laminations which are stacked up to be 1 meter or 2 long. There are also magnets that have these cross-sections here, so-called quadrupole magnets. Again, the vacuum chamber goes through the middle. The beam goes down here. There are even more sophisticated magnets with 6 poles shown here. And you see some of those magnets here. This is, the green is the sextupole, the blue is the quadrupole, or maybe vice versa, I can't tell. I think actually this has 6 poles and this has 4. You see these magnets being assembled here. It took many years to develop the design and construction of these magnets. They were then all installed. Here's what the completed system looks like in this very nice photo. And some of you may have, we had a dedication ceremony at the end of January, and at that time there was a new slip.
Also, the new piece of equipment on the peninsula literally making Bay Area businesses move at the speed of light.
You're watching NBC 11 News.
Speaking of moving fast, how about the speed of light? That's how fast tiny electrons fly through the newest machine at Stanford's Linear Accelerator Center. Here's how it's making Bay Area business faster and more efficient. This is the path an electron takes as it travels through the newest power source at the Stanford Linear Accelerator Center. travels, by the way, at 186,000 miles per second.
650 tons of hardware.
SLAC's new piece of cutting-edge machinery is called Spear 3, a quarter-mile-long accelerated circle of light.
This new machine allows us to make a much more bright light source.
It's an electron and magnet-powered light source that will help chemists, scientists, even chip makers become more efficient by measuring the behavior of electrons 100,000 times smaller than what we can see with our eyes.
Using fine X-ray beams, you can ask those kinds of questions, and you can get answers to those questions that then help improve the technology.
Spear 3 is an international effort helped along by
Notice
$58 million in funding from the Department of Energy, which expects a widespread return on its investment.
Chemistry, material sciences, physics, biology, environmental science, geoscience. There is virtually no area of science that is untouched by the light sources.
It's online 24 hours a day, 7 days a week, helping the technology industry move faster than ever. From design to construction, Spear 3 was 4 years in the making.
Okay, I hope you enjoyed that. I think the most interesting part of that was the number of applications that the Department of Energy official rattled off at the end. Pat Deemer, the woman that you heard, these are the areas that she talked about: chemistry, material science, physics, biology and biomedicine, environmental science, geoscience. But there are actually many subfields of these. So it has extraordinary application because X-rays, ultraviolet light that come out of these machines are used in so many areas of research. I'd like to go through quickly a few of these and point out that some of the lectures that are coming up in this public lecture series and tours that you can take of the laboratory will give you a better detailed idea of these kinds of applications. So in the area of biomedicine, back in 1986, we started a program in which we were able to image a human coronary artery. We did coronary angiography without a catheter. The X-rays are so intense that even though we don't give much of a high dose any more than it's done with the conventional facility, we do it without a catheter. And we could get information about blockages in coronary arteries that way. Again, studies were made related to osteoporosis, which is the weakening of bones after estrogen loss. A healthy bone has the strength that it does due to the connectivity inside the bone, which gets lost after estrogen loss. So this kind of picture, which can be taken non-invasively actually, with synchrotron radiation, was very important in giving medical researchers the understanding about osteoporosis. Studies like this actually make use mostly of the penetrating power of X-rays rather than the short wavelength. I'd like to get into the short wavelength part of it in a little later. But in the area of material science, I showed you the silicon wafer. That's merely an 8-inch wafer. Here is a state-of-the-art modern 12-inch wafer. That's what the industry uses now. And as they go to larger wafers and smaller feature size and faster chips, the need to have these wafers very clean. You notice this person is dressed in what we call a bunny suit in a clean room, and these facilities that make these chips and use these wafers are done in clean environments. As the speed of chips gets faster, as their density goes up, as more and more are packed into a single chip, the sensitivity to contamination or dirt of any kind becomes more critical. So industry needed to develop ways of understanding what the source of the contamination was and how to develop manufacturing techniques that would make the wafers even cleaner, and they could do that with synchrotron radiation. Many other applications. I don't have time to go through them all, but you can use synchrotron X-rays to visualize the magnetic bits, the ones and zeros on a hard drive. You can understand the nature of high-temperature superconducting materials. You can make extremely small objects, miniature mechanical and electromechanical devices. Shown here is a simple gear, but a very tiny one. You can make more complex devices, essentially devices like which measure pressure, flow, temperature, that fit at the end of a catheter. They're so small and can be inserted into the human body in a very safe way with a catheter to make measurements of functions inside a body. And to make these very small objects, synchrotron radiation is essential. You can also study the nature of damage to aircraft turbines when debris hits it. An aircraft in flight, if something enters the jet engine, it can damage it, and that causes failure later on. Understanding that can be done with synchrotron radiation. In the area of chemistry and biology, you can measure very low levels of mercury in fish and determine the chemical form. This is very important. You all may think, and it is true, that mercury is not a good thing to have. You want to avoid mercury, and fish tend to concentrate mercury. But the important thing is some forms of mercury are more dangerous than others. What is the precise chemical form of the mercury? What is its near neighbors like? How is it coordinated? Because that determines the degree to which your body metabolizes it or just passes it out without causing a problem. So to determine the chemical form of mercury and other nasty materials, various things like chromium and arsenic, you want to know what the chemical form is. I'll come back to this in a minute. But now getting down again to the atomic level, synchrotron radiation can give you the detailed structure of things like cholera toxin, anthrax toxin, and knowing the detailed structure enables you to understand the ways in which these toxins work and develop countermeasures. So we can actually determine the detailed form. These are atoms or clusters of atoms that make up a cholera toxin. And once this shape was understood, it was known that it kind of landed, almost like a lunar landing module, on the surface of the intestine or stomach and attached to certain receptors on the surface there and injected the toxin. Fairly nasty process, but once you understand it this way, you can try to develop countermeasures. I mentioned Julia Roberts. Here's the Julia Roberts slide, okay? You may have seen the movie Erin Brockovich, but that was about chromium in water. The question that was posed there was, what was the form of the chromium in water? Was it trivalent? Trivalent chromium, particular form actually shown here, is not a big problem, whereas hexavalent chromium is deadly. It's carcinogenic, and you want to avoid that. So that was the basis of the movie. Here's a picture of Julia that is part of the publicity. And it turns out that with synchrotron radiation, if you want to know what the form of the chromium is, you just take a small sample of, say, this water and tune into what we call the chromium K-edge and take in minutes or seconds a spectrum, and that shows it's essentially a fingerprint. In one case, it's the trivalent form. One case, it's the hexavalent form. And you can distinguish it very easily. So determining the detailed chemistry is what we do with synchrotron radiation. In geoscience and environmental science, we look for understanding of the problems. For example, problems that have to do with uranium that's leaking into groundwater. During the Cold War, the US had many bomb plants which made all kinds of nasty materials. And the pressure to make these weapons and develop them was so intense that very little attention was paid to environmental concerns. Instead, stuff was just dumped into tanks. Those tanks are now leaking, in some cases close to aquifers, which supply water to populations. So ideas are being developed on how to deal with uranium that may be leaking into groundwater. And one of the ideas was to dig a trench and put material in, essentially bone ash, and that might react with the uranium and prevent it from going into the drinking water. So what you want to do is understand how what kind of material might be put in here and how it might work. This was studied at SSRL, and now a trench is being dug and a giant underground filter is removing uranium contamination in an aquifer in Utah. In art and archaeology, we can use synchrotron radiation. There's a wonderful story about the Vasa. Some of you may know this. In 1628, the King of Sweden said he wanted to have the biggest and most powerful warship ever. Well, warships already had as many cannons as you could string along the lower deck, so they built a second deck and put a second row of cannons. They didn't bother to calculate the increase in the center of gravity, They launched this ship in 1628. It went a few thousand feet. A wind came and threw it over. It sank on its maiden voyage. Pretty embarrassing for King Gustav Adolphus, I think, at the time. Well, it sat in the brackish waters of Stockholm Harbor for over 300 years, and it was rediscovered 10 or 15 years ago. And remarkably, it was perfectly preserved. Somehow the water, the brackish, no organisms could live in that sewage that was being dumped in there. And so they decided to bring the ship up. They brought it up painstakingly, reconstructed it, put it in a museum. It's the most popular museum in Sweden. Those of you who may have been to Stockholm have probably been there. Remarkably, after a year or two in this museum, the ship started to disintegrate. After 300 years in the water, perfectly preserved, it couldn't take it in the moist atmosphere in Stockholm. And the question was, what's going on? What's causing the damage to the wood? Small piece of the wood was taken, brought to Stanford, put in the X-ray beam, and the detailed chemistry, which led to the formation of sulfuric acid, was elucidated. And now countermeasures are being used to prevent that sulfuric acid from forming. So again, understanding the basic science, the basic chemistry of what is behind a process enables you to develop solutions. In art, we're now talking to people at the Cantor Art Center on the campus. They want to restore, they are restoring a Renaissance panel painting. It's not clear who is the painter here. So they're doing all kinds of studies. They're using actually X-rays from the campus. Dr. Mendelsohn, who's here, actually has taken some very nice pictures of this complete painting using CT machines, just passing the painting through an X-ray CT scanner. We may take pieces of this, tiny pieces of this painting, in order to determine the detailed nature of the pigments, the technology that went into it, in order to understand as much as we can as this painting is being restored, and try to answer the question whether the painter was Jacopo di Salio or Filippino Lippi. It's uncertain, and they want as much information as they can get. So that's a broad brush. I'd like to go into more detail about one particular technology, one particular technique, because it's so important in understanding proteins. Proteins are very important, and what we do with it is a technique called X-ray diffraction. What is diffraction? Basically, the short answer, it's what happens when any wave strikes an object. It can be a light wave, a water wave, a sound wave. Here's an example. If a wave hits a simple object, here's an animation of a wave approaching a simple object, namely two slits. The wave propagates through the slits, and you get these patterns that you may have seen. Water waves do this. Sound waves do this. Imagine if you're just observing the waves out here and you don't know what caused it, you might be able to deduce in your mind that this kind of pattern of waves is due to two slits. In fact, you can mathematically analyze this pattern and deduce what caused that pattern to be made. So the diffraction, the pattern of diffracted waves reveals the nature of the object that caused those waves. Here's another example. If there's an X-ray beam striking an array, a two-dimensional array here, and you rotate that, then the waves come off in different directions. And you get spots on a screen, say film, that can record it. And if you analyze these dots, you can figure out that something of this nature caused the diffraction pattern. In a more complicated way, you can take entire molecules and pack them into crystal arrays, regular arrays, thousands, millions of them, in a crystal. And if you put that crystal in an X-ray beam, as shown here, here's a crystal and an X-ray beam hitting it, then you get a very complex pattern shown here. This is a diffraction pattern, and these are the spots made by the X-rays. Well, it turns out that if you then take many different orientations of the crystal and many different patterns, you can mathematically analyze these and go back and determine the detailed nature of the objects that caused this diffraction pattern. It's a way of seeing the detailed atomic arrangements in the molecule. Why is this important? It's particularly important for proteins. As you know from all the news that went on a few years ago, there was the sequencing of the human genome. The human genome provides the code by which the body makes more than 30,000 proteins that are essential to life. Proteins are very important. It's where the action is in living systems. They are motors, pumps, chemical catalysts, all these things listed here. They are essential to life, human life, and all forms of life. Well, we know the code, but knowing the code for proteins is not enough. It's like having a list of the actors in a play, but you don't know the plot or how these actors fit in. We need the detailed structure of each protein, not the code for it, which is a simple set of instructions, but we need to know where each of the atoms in the protein is, what the detailed shape. I showed you that in the cholera toxin, how you can understand how that works if you understand the detailed shape. So we can then deal, if you know the shape of these proteins, toxins, etc., you can deal with genetic malfunctions and develop drugs to combat diseases. In other words, structure and function are intimately related. If you want to understand how a protein functions, understanding its detailed structure is essential. And synchrotron radiation is now the premier tool for determining protein structure. Here's a protein structure that was determined at SSRL of what is called RNA polymerase. It's the structure that enables the code for each protein to be used to make each protein. Very important biological machine, which was determined by a group on the campus here. And you can see the details. Those ribbons are collections of atoms, many tens of thousands of atoms. Here's another view of it, which I like even better, because if you look at this animation, it shows, it winds up showing this trench. You see this trench here. And by the way, I have a three-dimensional model. You can come up and look at this later. Here it is. If you look at this, you can see perhaps that trench. I don't know if you can see it there. But what this molecule does is inside the nucleus of the cell, it moves over, latches onto the double helix of the DNA, unzips the DNA, reads out the code on one of the strands of DNA for each protein, and transcribes that code into what's called messenger RNA, which then goes out and makes the protein, and then it rezips the DNA back together without damaging it. So nature invented the zipper well before we did. That molecule unzips and then rezips the DNA and takes the essential information out about each protein. So that will be a topic for future lectures, actually, if you want to know more about proteins and how diffraction is used to make proteins. Oh, I forgot about this. Here is a simple display of diffraction. Here's a simple laser pointer. Can you all see that? It's striking at glancing incidence on the scratches in a simple steel ruler. So this is another ordered structure, and when light, in this case visible light, strikes that, it is diffracted into those spots. From analyzing those spots, I could then determine the fact that these scratches are 1/8 of an inch or 1/16 of an inch apart, knowing the angle and that detail. It's a way of determining the structure that caused that pattern. Knowing the pattern, the diffraction pattern, enables me to go back and determine what caused that pattern to be made. Okay, we have pioneered here at Stanford, and now this activity of using synchrotron radiation has spread all around the world. There are facilities now, 54 machines in 19 countries, not only in developed countries of Europe, Japan, the US, but countries like Brazil, China, India, Korea, Taiwan, and Thailand. In construction, there are 8 new machines, including places like Armenia and Jordan, and 11 more in design. It's an immense activity around the world with, as I said here, more than 20,000 scientists using these facilities around the world. In the United States, the Department of Energy supports 4 major facilities, one at the Berkeley Lab up in Berkeley, one at Argonne near Chicago, at Brookhaven on Long Island, and of course University of Wisconsin, and 2 other small machines, one in Louisiana, one in Washington. So we have 8 facilities in the US, and there are 50 or so around the world. The largest facilities outside the US are this 6 billion volt European synchrotron radiation facility in France, a half-mile around, a huge machine, which is one of the most brilliant machines in the world. It's shared by about a dozen countries that get together and work collectively on this. It is an international project. The biggest machine in the world is in Japan. It's an 8 GeV. The Spear machine, by the way, is only 3 GeV, but we have very clever ways of using that to get very good radiation out, even at high energies. The Japanese machine is a mile in circumference, and it runs at 8 GeV. Cost about $1 billion. But there are smaller machines all around the world. For example, in Thailand, here's a small machine that's maybe 20 meters in diameter that's in operation now. Here's a machine in Brazil. This is about 5 or 6 years ago, before the beam lines were put on it. But you can see the bending magnets, the various other magnets, and the vacuum chamber that goes through it. It's wonderful being in a field where you have colleagues all over the world. You get a chance to travel and meet with them. And you also share not only your interest in science and learn things from them, but you also get a different perspective on the world sometimes from them. Here's how the Brazilians view the world. Another facility I'd like to describe briefly is the Sesame Project, which is a collection of 9 countries, essentially Israel and 8 Islamic countries joining forces in this day and age. Can you imagine that? To build a synchrotron radiation facility which will be located in Jordan and provide radiation for scientists in the region. This is what is being planned there, and it's under construction right now. It'll be a very powerful machine. It's a project that's sponsored by UNESCO and very much supported by Jordan. Here's the King of Jordan, the Director General of UNESCO, congratulating each other at the groundbreaking ceremony a little over a year ago. This project is well underway, and remarkably, you might ask, people ask me, why a synchrotron facility in the developing world? Well, they have answered this question themselves in countries like Thailand and India, Korea, Taiwan. Many reasons. It provides world-class basic and applied research opportunities. It trains graduate students who no longer have to go abroad for this frontier training. It attracts their scientists, their nationals who are working abroad because they want to do frontier research to come home, reversing the brain drain. And as I showed you, it can address biomedical and environmental concerns, some of which are regional and can be best studied in the region. So all regions of the world, in a sense, need access to such a facility. It promotes the development of high-tech industry, so-called capacity building. But perhaps most important, particularly in the Middle East Sesame Project, is to use scientific cooperation to promote peace and understanding between people, different traditions, religions, races, political systems. What is the future of synchrotron radiation? We intend to continue innovating. We have developed the first major synchrotron sources, the wigglers, the undulators, the technology of using these in the beam lines and in the experimental stations. And we have ideas about continuing to innovate. The main innovation is to now use the linear accelerator itself, not the storage ring, to generate an extraordinary light source, an X-ray laser. And it will provide very intense, even more intense beams of X-rays than the wigglers and undulators in machines like Spear. But the important thing is that these will be ultra-fast flashes of X-rays in so-called femtosecond pulses. A femtosecond is 10 to the minus 15 of a second, or 0.00014 zeros in a 1 of a second, a remarkably short time. It's a millionth of a billionth of a second. It sounds ridiculously short. Nothing important can go on in that short a time. But in fact, that's the time constant for chemical reactions and biological processes. If you want to understand chemistry and biology, you need to understand what's going on that time scale. This laser will start operation in 2008, another first for SLAC. Why is it important to take these short flashes? If you want to stop the action, here is a photograph taken perhaps at a 500th of a second, maybe even a 1,000th of a second, I'm not sure. The ball is blurred, it's moving very fast. The subject is frozen, but we don't get enough information about fast-moving objects. We need something faster. So in order to stop action, here is an interesting video of a bullet going through a pane of glass. Each of those frames is taken in about a few millionths of a second. So if you want to understand fast processes, you have to have a fast flash of light or a fast shutter speed. You can't make shutters go at a millionth of a second, but you can make light pulses actually go that fast. Fast action studies are a long tradition at SLAC. You may know that back in 1878, Edward Murbridge took these remarkable pictures of a galloping horse in order to settle a controversy. Do all four legs leave the ground at any one point? And as you can see, some of the images he took clearly answered that question. Here's one of the images. If you put them all together, you can make a simple movie which shows that galloping horse, and there, all four horses are off the ground. So we want to do studies now. We're opening up the ultra-fast time domain. How far does light? Light is the fastest thing in the world, 186,000 miles a second. How far does it go in 1 second? How far does it go in a femtosecond? In 1 second, light goes around the world 7 times. That's a long distance. How far does it go in a femtosecond? It goes 3,000 nanometers. But a nanometer is so small that this is 1/10 of a human hair. That's the speed with which we're trying to freeze chemical reactions and biological processes. The way we do it will be to modify the last kilometer of the 3-kilometer LINAC and make a very intense electron beam, which will then go through a 100-meter-long permanent magnet undulator and generate these bursts of light. In order to make that light very intense, we need to teach the electrons to radiate coherently. This is shown in this slide here. This is a snapshot, a computer simulation of several thousand electrons. This the width of this beam is 1/10 of a millimeter in the scale, very small, a little more than a human hair in diameter. And this is the axis in which this thing is going down the undulator. And look what happens according to computer simulations. The beam goes down, it breathes due to the focusing action of various lenses along the way, and roughly halfway down, say when it's 30 or 40 meters, the electrons start to congregate together. And when electrons collect together like that, they act like one fat electron, and they radiate much more light than individual electrons do. So that's the secret by which we will make these short pulses of very intense light, and that's what we need. Coherent motion is all we need, and that's exemplified here. So if you tune in and come back here in about 2008, if everything works the way we expect, we will make these very short electron bunches, and we will slam them into molecules, a sample, and we will study things like molecular bond breaking, which takes place on a femtosecond timescale. Here's a bond that's broken. You see this little red structure here, which is leaving another larger object, and you can take stop-action movies this way. I think Murbridge would be very proud of us. I'd like to give acknowledgement to the sources of the funding that make all this wonderful work possible. It's really the Department of Energy. The U.S. Department of Energy Office of Science supports high-energy physics. Basic Energy Sciences supports the Synchrotron program. We get money from the National Institutes of Health and some of these other places. We want you to help us inform government officials, agency officials that we're doing good work here. Give us more money, we can do even more. I'm told that I should remind you what I talked about, so here are the questions that you'll be asked about by various staff members that accost you as you leave, and remember that last question here. As Neil said, We invite you to come back. There are tours. Here are the ones listed for the month of May. You're all invited to come here. And the public lecture series continues on till the end of this year. 4 more lectures are scheduled. The ones in red, actually, have to do with X-rays. So if I've whetted your appetite about X-ray research, you can learn more from these 2 talks here, plus talks about matter and antimatter. This is elementary particle physics and particle astrophysics. These are all activities that go on at SLAC. We're very proud of them, and we want you to be proud as well. Thank you very much.
So, thank you very much, Herman. Outside, there are real physicists who you can go out and ask questions to. You will recognize them, I won't tell you how. There are also some cookies, some soft drinks, so please, if you'd like to go out, and if you have any questions, feel free to ask them. Also, there will be demonstrations down here of various concepts. So, make yourselves at home and enjoy the rest of the evening. Thank you. Thank you, Herman.